So, good morning, everyone. This is actually pretty early for me, so excuse me if I made any mistakes. And this is my first lecture. So, before I want to get to the actual studying of abstract algebra, I want to ask what's abstract algebra? Why do you study abstract algebra? Abstract algebra is the studying of algebraic structures. In, these algebraic structures, we often divide them into groups, rings, fields, and so on. So, but like some actually think that abstract algebra is the study of groups or the study of rings or the study of fields. Actually, I think that abstract algebra is broader than this, I would say, non-complete idea because it study structures in itself. I think we all used to the structure of the real numbers with multiplication and addition and powers and logarithms and exponentials and so on. We are pretty used to the algebraic structure of the real numbers. I assume that everyone here took at least one linear algebra course. The first time a math student encounters a non-usual algebraic structure is when we you see the structures of linear transformations or matrices. You see, if I want to, for example, multiply this matrix. Wait, 1 second. Yes, this matrix. Uh, 1, -1, 1, 0. By this matrix. Uh, by this matrix, 0, -1, 1, 1. In the first glance, you would say that like the naive point of view for the first time that you multiply each indices of one multiplying zero. At least that's the idea that I had when I first started the linear algebra. But like then you know that's actually wrong, and you have another way of multiplying matrices because matrices are examples of linear transformations, and multiplying two linear transformations is equivalent to making a third linear transformation from combining these two. Just multiplying each index in the way that you are used to in the real numbers is not enough. We have special operations called matrix multiplication, and you will actually find that the result of this matrix multiplication is the identity matrix. Where- yeah, is the identity matrix. Uh, Now you see that these two are inverses. Now, for a linear transformation to be the inverse of another linear transformation, say is meaning that it negates the change or the transformation it does. Now, we could actually, firstly, before getting to the abstract algebra, how do I know that this matrix here is the only inverse for this matrix? Uh, Trying every matrix there is to find an inverse is not actually very, very paying. But like, let's assume proof by contradiction. I assume that you are familiar with it. Uh, let's assume that this matrix A has two inverses, B and AC, which both gives the identity matrix. Now, by that, I'm saying that I can make sure that B and C are equal with uh, B multiplying both sides by B, so it will be BA B equals BAC equals the identity. Now, with association, I can group this BA and this BA for each one to equal the identity matrix in itself. So IB, the identity equals IC equals B. So we're canceling out the identity. So B equals C equals B. So that's contradicting the first assumption that that B and C are distinct. That's a nice proof. But notice that I didn't use any properties of matrices here except that they are associative and they have an inverse. And I used and my by multiplication here, I don't mean the normal multiplication, I obviously mean matrix multiplication. This algebraic structure we call a group. That's a group. Uh, Groups are the first structure that you study in abstract algebra because firstly it's the easiest, and secondly because it gets a lot from linear algebra. Like you will find out when you actually we will going to study linear algebra from an abstract point of view soon, but like you can see that any vector space is a group in itself uh, with vector addition. Firstly, before we discuss that, actually, what do we mean when we say there is a group? That's a group. A group must have a group is a set. A group is a set. Not any normal set. Uh, a set that is defined with a law of association. That is defined with a law of association. Before actually saying the rest of the group definition, I must clarify what is a law of association. A law of association in a set, doesn't have to be a group, is a map from takes two elements from the set and gives another element from the set. So A belongs to the set times, or let's denote it with that funky symbol, P that belongs to the set equals some element C that also belongs to the set. That's the law of association. The first law of association that I talked about is matrix multiplication. If you multiply two matrix, you will get a matrix. Vector addition is also um, is also uh, a law of association, because if you add two vectors, you will get a vector. That um, that law of association it says that the set, if the set has a law association, it's closed under that law association. So uh, that's not the only thing that we use to define groups. We use three more conditions to define groups. As you saw in the proof, all these conditions are here. Firstly, we said there, first things I said there is an inverse. So one for every element in the set, there an inverse. Now, the second thing I used was the associativity of matrix multiplication. So second, the law I will denote the law of association is as associative. Uh, Last thing I said was that there is an identity, and that identity actually commutes, and it doesn't alter the result when multiplying by an element of G. So I would say there exists an element E such that the G belongs to the group G. EG equals GE equals G. The inverse here, hmm, I didn't write that. The inverse G times G inverse also commute equals G inverse. G equals E. That's a group. That's the first algebraic structure that we are going to study in this course. You'll find from I see the rings and fields are just groups with extra conditions, but we will not get into that now. The first thing that you notice is weird about matrix multiplication after the weird way that you compute it is that it doesn't compute. Only the inverse and the identity matrix commute with another matrix. You see that uh, any matrices, any linear transformations matters which one you multiply first. Um, So for G, H does not equals each J. But like we are used to the real numbers or the integers where uh, the law of association there is a billion, like both multiplication and addition are for the real commutes. So, for example, if the integers is actually a group under addition, you see that for every element in the set there is an inverse. So for every A, for every A, there exists negative A. And the law of association is associative. You see that A plus B, if I add to it C equals A and I add to it B plus C. That's the meaning of associative. And there is an identity with zero, where A 0 plus A equals A plus 0 equals A, and negative A plus A equals 0, the identity. That's a group. But like, there is one more condition to it, like A plus B equals B plus A. Is that a distinct structure? Actually, no. Kind of not. It's an abelian group where abelian is named after Abel, one of the founders of abstract algebra and group theory. So it's named after him. So actually, this is why you will find that abelian is right is wrote with a capital A in honor of Abel. Uh, Another abelian group is vector space. Is there any vector space? You see that adding two vectors doesn't matter in the order that you add them. If I add the vector A and I add to it the vector B, it doesn't matter if I add the vector B, then I add the vector A as long as their magnitude is equal, and I'm not very good at drawing that. Now, when we study groups, we notice that uh, there is actually an interesting property that we see, that there is a general group. There is always a general group, like there is a bigger group than the one that we're studying. The set of invertible matrices, often denoted by G, L, N, R, N here because it's a subset of a kind of subset of Rn. The matrices in Rn. N by N matrices. Now you see that when I studied linear algebra, I asked myself, now that's the linear, uh, these are the linear transformations, but like, what about nonlinear transformations? For example, if GL1R is basically the real numbers, uh, it stretches or contracts the real number line in a linear form. So, then what about, like, for example, that map that f of x equals x squared? It's actually a map. It's a bijective map. Like, I know that some people have problem with the vocabulary. We define the group a bijective. Bijective equals injective plus surjective, which only confused you more. It's actually means that what I said means that it's 1 to 1 and onto, which actually means that every uh, every x has an x squared, and every x squared has a root x. So it's 1 to 1. Every number gets mapped to a real number in the set of the results, and every member of the set of the result have a member that produced it in the set of variables. If you, I hope that clarified it. Bijectives is 1 to 1 and on. So getting back, f of x equals x squared, that's a bijective map. So what about it? Like, why don't we study it? Actually, from this you will find that there is a more general group, which is the set of all bijections G, where G equals the set of all bijections G from T to T. Mm, that's often G is often denoted by the symmetries of T. We must be sure that's actually a group before discussing it. You see that every function, every bijection uh, has an inverse, like the example that we did for f of x uh, equals x squared. There's an inverse. Um, let's call g of x, where it is the square root of x. Now, so if to prove that's an inverse, so f of g of x equals g of f of x equals e of x. Here's e of x equals x. By the way, e is from the German word eins, meaning one. Um, that's an inverse. The We see that the law of association here, of law of composition here, is actually the composition of functions, the composition of bisections, or composition of transformation. And there is, of course, the identity bijection, or the identity function, or the identity transformation, whatever you want to call it. You can see that um, actually, you can see that this set the symmetries, you can see that the symmetries of Rn is the big group that is that GLN, the general linear group of order n, R, is a subset. Yeah, is a subset of it. Is a subset. Is a subset of it. So actually, yeah, for the people who are in on Zoom, we are going to run out of time in 10 minutes. I will resend the link in the group, but let's continue now. Okay, so that's a subset, of course. We know that the symmetries of Rn is a group. So any set any set that is a group, any subset of it is going to be a group too? Actually, no. We can actually define what is a subgroup. Now, a subgroup is a group with actually three conditions. Uh, it must be actually you can see that it's a group, but like the for every element in the set there is an inverse. So so for every G there exists the inverse of G. The law of association is associative. That's actually from the group. That's the only condition that is passed. Any subset of the of a set that is a group, the law of composition or association is also associative for any subset, even if that subset is not a group. So the law of association is associative. That's we don't need to write it, and and the identity is a subset of the subgroup H. The third condition is closure under composition. So if I'm going to get a if I'm going to multiply any two elements from the subgroup H, then the resulting element must be an H. Now there's an interesting group that's called the permutation of n letters. That's also a symmetric group. Like it's denoted as n, which is the permutation of the set 1, 2, 3 to n. For example, um, 3 is 3. We have six elements in it, like 1, 2, 3, 1, 2. This one takes 1 to 2, 2 to 3, and 3 to 1. We call that sigma, as Professor Benedict Gross denoted it. That's the cyclic permutation, 1, 2, 3. And there's also this cyclic permutation. Yeah, one maps to three, so two maps to one, and three maps to two. That's sigma prime. There's that one to one, two to three, and three to two. That's we call that tau. There's one to two and two to one, and three is constant. We call that tau prime, and there's uh, we can also one maps to three, three maps to one, and two maps to two, and that's tau double prime. And that's there's of course the identity permutation, one maps to one, two maps to two, three maps to three. That's a group. You can check that that's a group from the laws that we stated before, and we actually applied it quite a lot. Now, what's interesting about this group? This is the first group like that's easy to visualize, easy to see, but it's not appealing. Uh, so there's appealing. The appealing. How how can we see that it's not appealing? Take for example sigma and tau. Uh, Sigma and tau. We can compose them in this way. Um, Sigma of tau of one, for example. Uh, Tau takes one to one, so it will be sigma of one. So sigma takes one to two. And sigma of tau of two. Tau takes two to three, so it will be sigma three. So which is one. So we see that two, three. We see that sigma tau takes one to two, two to one, then it must have three as a constant, which is actually tau prime. So sigma tau equals tau prime. That's good. But what about tau sigma? Tau sigma of one, sigma takes one to two, so it will be tau of two. Tau of two is three, and tau of sigma of two equals sigma of two is actually three, so it will be tau of three, and tau takes three to two, so it will be two. So that map takes two, three, takes one to three, two to two, then it must take three to one, which is tau double prime, which is equal to tau sigma. You see that tau sigma doesn't equal sigma tau, so it doesn't commute, so it's not appealing. Actually, any group of any symmetrical group Sn of more than 2 is not abelian. We stopped last time by asking that how can we prove that Sn uh, more than 2, greater than 2, is non-abelian. Uh, to, to prove that, we can see that we can use a property that uh, the Sn is has a subset Sm if m is less than n. So S3 is a subset of S4 is a subset of S 1 million. And for a group to be a non-abelian, only one element of two elements of it must not commute. If these two elements doesn't commute, then the whole group is not abelian. So as we prove that S3 is not abelian, with this we have proved that S4 is not abelian, S5 is not abelian, S6 is not abelian, and so on. So the permutation group is not abelian. That was one interesting uh, groups to study. Now, uh, you can see uh, you can see that another example of subgroups uh, are matrices. We talk about matrices a lot. So we have discussed G, L, and R, which is the set of all invertible matrices. But what about like the set of matrices that stabilizes the we will talk about S2R, not SN now. That's a big enough group to talk about. Now we can have uh, a set a group of matrices that stabilizes the the x coordinate, the x-axis. Now we can also have a matrix that stabilizes the y-axis. We can have symmetric matrices. Uh, we can have matrices that are in this form, multiples of the identity matrix. Each one of those is a subgroup of G and R2. If you can check that their law of association is associative in GLN in GL2R. So it will be a group. There exists an inverse. There exists an identity, and each subgroup of those is closed under matrix multiplication. Now, uh, there are sometimes there actually times we can see all the subgroups of some of a specific group. But notice that I said sometimes. It's not I cannot infer from the axioms of a group only that every group I can determine its subgroups. But it's good to see what a subgroup is. Uh, and when I can identify all the subgroups of a specific group. We know that the integers uh, under addition forms a group. You can see that the multiples of the any multiple of the integers under addition also form a group. This is why, like, I am. This is like a hint at modulus arithmetics. We will get uh, we will get to it next week, but like we have a hint of it, like in the even and odd arithmetic, like 2z plus. We know that this only has 0 because that's the identity. 0, 2, 4, 6, and so on. This is closed. Addition, like you must memorize the axioms of a group so that you can apply them quickly. Like the law of addition is associative and it's commutative. There is an identity plus or minus 2. There is an inverse, so and it's closed. If I if I add two even numbers, I get an even number. If I subtract two even numbers, I get an even number. So it's closed. Actually, this also apply to any integer. So it will be, for example, 3 multiplying by any numbers that divisible by 3, plus or minus 3, plus or minus 6, plus or minus 9, and so on. That's also closed, and you can check that. Now, to prove that for any p, for any v, that this group is actually a group, we can see that uh, if my uh, if minus b of n equals b minus of n, we can see that b0 equals b0. And of course, the law is associative. And for closure, I can see that b n plus b m equals b m plus n. That's the distributive law. But now we showed that every b is a subgroup. But how can we show that every subgroup are in the form of BZ? Now we have two probabilities. We can say that if there is subgroup H that is in the 1, H is equal to the identity element, which is equal to 0, Z. So we prove that. Now, if H doesn't equal the identity element, then so it contains uh, m doesn't equal to 0 belongs to H. Yeah. So let's say that okay, let's say that P is the smallest integer such that belongs to H. Now, uh, suppose that we have H that's in the subgroup. From the Euclidean algorithm, I can say that H equals MB plus R, where R greater than or equals 0 uh, and less than B. Now, for R, for any BZ to, for any subgroup to be in the form of BZ, then R must be equal 0. So I claim that R equals 0. Why not non-zero R? Because from the Euclidean algorithm, I can see that R equals H minus B. That's in H. So R is less than B, which is not, which contradicts the assumptions that we made that B is the smallest integer. And as H is a subgroup of Z, then all of it must be integers. So R must be an integer. And so the only small integer smaller than P in H is 0, so R is 0. Then that's it. That's an easy proof. Uh, Now, the cyclic, we have a new type of subgroups which is called cyclic groups. Cyclic groups are actually pretty fun and pretty nice. A cyclic group, if G is an element of the group G, then there is a subgroup H, which is denoted like this, of the element G that's called the cyclic group of generated by G. This is the smallest subgroup that contains G. Uh, that is written by, I can write it G to the power of M as long as M is in the integers. That's a subgroup because let's actually check from the laws of groups. We know that uh, there must be an identity. So G would be equals to G to the power of 0 would be equals to E. So there is the identity. There is inverses. So for every G of M, there is G of negative M, where if I compose them, I get the identity. So there is the inverse, and the law of association follows. So and closure, because if I multiply G M multiplying it by Gn or composing it by Gn, G to the power of n, then I will get G to the power of n plus n, which is in the group because it's all integers. So it's a subgroup. Cyclic groups are important. So uh, it's it's important to focus on it and to actually understand it. And one important thing to understand in the cyclic groups is that it doesn't have each word doesn't have to be distinct elements. Now, we discussed uh, this. Uh, I want to get that better. One second. Yes, we discussed S3, and we can see that we can construct a cyclic group of for the element tau. Now, um, we know that for H be a cyclic group generated by tau. So tau to the power of 0 equals the identity. Tau to the power of 1 equals tau. Tau to the power of 2, if I 2 goes to 3 and 3 goes to 2. Now, if 3 is 3, will then goes back to 2 and 2 goes back to 3. So it will be the identity again. So t to the power of 2 will actually be the identity. That's a subgroup. That's a subgroup. We proved that any group generated by any cyclic group generated by G is a subgroup. Anyone with the laws of exponents and so. Now, I can see that because I can see that here because if I multiply it by tau one more time, tau to the 3, I will get tau again. If I multiply it by e, then I will get tau again. If I multiply it e by e, I will get e. So it's closed. Um, so that was important to mention. We will not see right away its application. I don't think we will see its application now, but it will be important, very important actually in next week discussions.
Hey, Mohammed, there was a question in chat that I think might be interesting to bring to the whole group.
Yes.
Jamama asks if for cyclic groups, every element has to have a power that's equal to the identity. Can you comment on that?
Uh, I couldn't hear you well. Can you repeat it?
Yes, I can, but it's also in the chat if you'd like to pull that up.
Yes.
Jamama asks, for cyclic groups, does every element have to have a power equal to the identity?
Actually, no, no, no. I said for cyclic groups, that's the definition of cyclic groups. That's the definition here. Cyclic groups are by generated by the element G contains all powers of G. Now, I said that the these elements, these powers cannot can be not distinct, can be distinct. So as I said, there's there's tau to the power of 1, tau to the power of 2, tau to the power of 3. Any even power is the same, and even all power is the same. That's in only special groups, but like I think I don't know if these special groups are more than the normal groups or not. But I think that you will diverge often. Now, let's see an example when we diverge. If G is integers and H uh, is by 2 is generated by 2. Now, notice here that the power is not the multiplicative power that we have in the real elements. It's actually the repeated addition, like, so it will be uh, 2, so it will be 0, then 2, then 4, then 6, then 8. I will not get back to 0. That's a cyclic group, and that's that generated by 2, and that diverges. So any it doesn't have to converge back to the identity or back to the element. Yes. So if you have actually any other questions, like please ask them now before we get to the isomorphism and wrap up. Does it repeat by equivalence classes? Equivalence classes are not discussed yet. It will be, I think, in next week. In the next week discussion. I don't want to mention them now to not. No, no, but like actually DM me on Discord and I will answer your question there. Are there any questions you want? Anyone want to ask? Yeah, yeah. I will post it. I will post it on the group. But like, can equivalence, it's a nice question because equivalence classes actually will get us and cosets and so will get us to an interesting places. We will see that actually the cyclic groups order. Yes, you reminded me of something. Now, the order of an element. Now, uh, for the order of the group G equals the number of elements in it. Now, the order of an element G is the number of distinct powers uh, in its cyclic group. We saw that tau here has only two distinct elements. So tau has an order of 2. Actually, if you saw sigma for the cyclic group of sigma, you will see that it actually has the order of 3. Uh, order you can see that the order of the elements of the group actually divides the order of the group. We will have some interesting stuff by this. So if I actually got into the rabbit hole of equivalence classes, I will discuss next week discussions today. But it's a nice question. So wait, so the order of elements of S uh, wait for I for I have to make sure of that, but like for example, S4 has 4 uh, 4 factorial elements, so it will be 24. Yes, I of the order of elements must divide the order of groups. Yes, yes, that's the general idea. The order of elements of Sn is n minus 1. It actually no, like tau is element of 2, has the order of 2, and sigma has the order of 3, which is f. That's not the discussion here. The discussion is that the order of you see sigma and sigma prime has the order of 3, sigma tau has the order of 2, tau prime has the order of 2, e has the order of 0 if you want, or 1 has the order of 1, not 0, sorry, has the order of 1. You see that 1, 2, and 3 all divided in the order of S3, which is 3 factorial, which is 6. Now for S4, it's the order of all elements, so it must divide 24, which is the elements of S4. Any other question? Actually, Stucky, you had the questions from last time. Any interesting questions?
No, it looks like you've caught up to chat.
Yes, okay. Any other question? By the same thing, he has to be an element of all n minus 1, or not necessarily. No, I don't think not necessarily, because Sn, yeah, n1 does not divide n, so actually no, no, for n minus, the, I don't think you understand. You see, the subscript n here is just the number of the set that we are talking about its symmetries. It's not the order of the set. It's not the order of the set. You see that S3 has order of 6. The n minus 1 divides the symmetric groups because n is not the order. N is the look for Sn, that n you're talking about. So equal has the order, that's the order, has the order of n factorial is equals n multiplying n minus 1, multiplying n minus 2, and so on. You see, that's the n minus 1 that we are talking about, that divides n. That n is not the order. That n is the number of elements of the set that we are permutating. So Sn is a symmetric group of n elements. n1 divide that because the order of Sn is n factorial, which is n multiplying by n minus 1 multiplying by n minus 2, and so on. Did you get that? Yes. So, do we have any other questions before going?
Yeah. Has a book up to this point covered Lagrange's theorem, or is that still coming up? I haven't really been reading, to be honest. But
No,
I read
no.
this like several years back, so I'm just kind of
Yeah. So it's fine. Lagrange theorem uh, is discussed in chapter 2, but like not yet.
okay.
Maybe
Yeah,
next
no, I was
week.
just asking if like that would be useful as explaining the
Yes,
whole
yes, that will be
dividing
very
order and
useful.
stuff. But I don't want to be too quick to jump here. So
Yeah,
okay,
yeah.
cool. No, that actually just answered my question. I think that's all.
Yeah, so thank you for the questions. That's all. That's actually the reason I didn't answer the question about classes of equivalence and cosets, because we will get to the Lagrange theorem discussing it. You can actually actually I don't know who will be the presenter next week, but I think I may volunteer to present next week too, alongside with the presenter of the week. But the presenter of the week will explain to you what is Uh, what is the reading of the next week, and most probably Lagrange's theorem will be in it. So, any other questions? Should there be another section for proofs or for every or most?
Yeah, sure. I got another question. What's kind of the goal or like the difference between these versus like watching the lectures? Like what's like is there like a specific
Yes, I will
difference?
answer. Okay, I'll answer
Yeah.
Kevin's question first. Uh, we didn't have any much of theorems. Now it's all propositions, and I will post the lecture notes. It's actually not written by me. I think it will be redundant to write my own notes. Hmm, it will be written by Benedict Gross and Peter Green, actually, who made this course. And from this question, I will answer Mira's questions because these meetings offer a kind of more insight and interactivity for people who wants to ask questions or get the explanation in a different way. And yes, they may not be crucial now, but they will be crucial when we get to the chapters that actually Benedict Gross and Peter Green skipped. I have the book with me right now. I think uh, Peter Green, Professor Benedict Gross, skipped bilinear group forms, linear groups, group representations, fields, and Galois theory, which I think are crucial part of the book. So
Cool.
this
Yeah, that makes sense.
yeah,
Thank you.
this lecture will get more and more important as we go further in the book. So, any other questions? Uh, it's too fast. It's too fast. It's asking about questions that too further in the book. But like, if you want me to send you up a copy of the book, I will send you. But like, let's calm down on the question for further for future events. I think the question in the material is over. I will end this meeting right now for the hopes that I don't have to wait the 10 minutes between meetings. And we will get back to discussing isomorphisms and finishing up what we have done. Thank you very much. Okay, so continuing I assume continuing what we have about groups and isomorphisms. We talked about, as I mentioned, abstract algebra is often known as the language of modern mathematics. Uh, and I've talked up in the beginning of the lecture, I talked about that abstract algebra is a study of is a study of algebraic structures, but like until this point, we just discussed the groups um, and some fun operations and results from studying the groups, but we didn't study the the structure itself. Now, isomorphisms is what is the most fun and the most interesting concept in abstract algebra. Now, in linear algebra, you have introduced mostly lately in the course to the concept that matrices um, represent a linear transformation. a linear transformation, but like that doesn't that doesn't actually be apparent until later. But like first, the matrix is a square array of numbers, and linear transformation is a linear transformation. How can they relate? How can they represent each other? And this question is actually this question is actually raised from primary school to the second year of mathematical of your mathematical studies. By for example, how can there be a negative two apples? How can there be a square root of two apples or pi apples? That is not apparent right away, but we we have we have get used to the concept of representing apples by numbers and linear transformations by matrices. Now, but like to really answer the question, isomorphism is the answer because isomorphisms are maps between groups that preserves the mathematical or algebraic structure. Now, for example of that, consider these two groups. The cyclic group of rho in S4, uh, rho is the cyclic permutation. Now, I can make a multiplication table of the cyclic group of rho in this format. And now consider this group, which is a subset of the complex numbers plus or one negative plus or minus negative one and plus or minus negative I. And the multiplication table of it is as shown. Now I can make a bijective map that takes uh, each element in the cyclic group of rho to an element of Ng, which is a subset of the complex numbers. Now, the meaning of preserving the structure is that if I take two elements in G1, it's a bijective map where it takes elements from G1 to G2 while preserving the algebraic structure. Now, the meaning of preserving the algebraic structure would be that to take two elements in G1 and multiply them and then map the result of their multiplication in G2. If that is equal to mapping X independently to G2 and mapping Y independently to G2 and then multiplying them, getting the same result, then these two groups are isomorphic and this function, the bijective function f, is an isomorphism. Now, there is a more general notion of isomorphisms or homomorphisms where f doesn't have to be a bijective map. Now, if the set of invertible matrices, as I mentioned in the beginning of the discussion of isomorphism, if the set of invertible matrices maps to the set of linear transformations from Rn to Rn, what would be a homomorphism from the invertible matrices in to some group? Can someone think of a homomorphism from the set of G ln R, the homomorphism, the normal, the invertible matrices to some other group? Can someone think of it?
Yeah, this kind of got buried in the chat, but Indium suggested the trivial homomorphism where every matrix gets sent to the identity.
Yes, that's work. But like there is more fun homomorphism than that. That what uh, what was uh, what was said is a perfectly good homomorphism, but it's not a fun homomorphism. The more fun homomorphism is the determinant homomorphism. The determinant of two matrices A and B is the determinant of A multiplied by the determinant of B. You find this map and this homomorphism quite early in uh, in your linear algebra course, except if you are taught by Sheldon Axler. But it's actually a fun homomorphism. There are, but like isomorphism have that extra condition of f being bijective. So actually, it's more easier to check than homomorphisms. Like if there are Peter Green in his lecture mentioned three tests to find if G1 is isomorphic to G2. So it will be one if the order of G1 equals the order of G2, then maybe this map is home, then they are maybe isomorphic. If G1 is abelian and G2 is abelian too, then maybe they are homomorphic. If their G1 and G2 have the same number of elements with the same order, then they are most popularly homomorphic. Now we define what is isomorphism, we define what's homomorphism, we can define it to what is meant by an automorphism to finish
Sorry,
the
Mohammed, can you write the beginning of that sentence on that slide? Uh, those are things that are satisfied when G1 and G2 are isomorphic. Is that what I'm supposed to understand?
yes,
Okay.
yes. The order of G1 and G2 must be the same. If G1 is abelian, then G2 must be abelian. If I will write this in a red, if and G1 and G2 must have the same number of elements with the same order. Uh, Now, automorphisms are just homomorphisms. Uh, where f is bijective, but it's from G to G. It's automorphisms. So it will be an isomorphism from the group to itself. Um, Now, actually, we are exceeding what the reading assignment of the week, but like it's the same lecture that I assigned, so I will just mention quickly what is meant by images and kernels. Now, In the map, the determinant in the homomorphism, the determinant of a matrix, we see that not all real numbers are included in the result. Like as GLN R, that's a map, the determinant is a map from GLN R to R. Here R is a group, and then R must be a group too. GLN R doesn't include the matrices with determinant zero because it's the invertible matrices only. Now R is the in the multiplication group of R because it doesn't include zero. It's a group. Now the image of R is the image of this homomorphism is all of R, all of non-zero numbers. No, that's the image. The image is it's often built in a figure. So if this is G1 and this is G2, then a homomorphism, because it's not it doesn't have to be bijective, so it may be mapped in just a small subgroup of the G2. That's the image. A question, a good problem to work on. I don't know its number, but it's in the problem form. Was to prove that the image is a cell, and actually, if there's as its subgroup, then there must be an identity element in it. Now there's something called the kernel in G1 that is mapped to the identity in G2, which this is called the kernel. The kernel of the determinant map is uh, all matrices of this form A0. Yes. I think that's all for discussion for my presentation today. I would like to take questions before the meeting ends again. So I will, if you have any yes, if you have any question, Stucky, did you catch any fun questions?
There were a couple of comments.
Yeah.
Um, the first, no, there was a question by Kevin Chavez who asks if the transpose is a homomorphism. Had some on like matrices, although I guess we could restrict it to be invertible matrices.
I think yes, yes,
Okay.
yeah. I think it will be an automorphism from GLN R to GLN R, I think. Yes.
Okay. Um, and then this one sort of got settled earlier, but maybe a subtlety that we came to appreciate is the determinant um, doesn't transfer the abelian property. Like the matrices are not abelian, but um, the real numbers are. But that's perhaps because it's a homomorphism instead of a
Yes,
full
yes,
isomorphism.
it's a homomorphism, like if you check the three or the three conditions, if you want to call it, for isomorphism, we saw that the order of G1 doesn't have to be equal to the order of G2. This is why we have an image. If G, it doesn't actually transfer the abelian property, and G1 and G2 must not cannot have the same number of elements with the same order. So I don't actually know if there are conditions to know if two groups are homeomorphic, but like check the homeomorphism relative. So I think there's no other questions, right?
Yeah, so far I think we're good.
Yes. So I wanted to know your feedback on the lecture. Um, this is actually my first lecture in my life. So
Well, congratulations.
so,
Where would you like that feedback given if people have some?
in my DMs and on the group here in the chat, and I would appreciate any feedback. Thank you very much.
Yeah, and thank you.
Thank you.
Everyone in chat is saying it, I'll say it too.
Thank you, and thank you for helping me throughout this presentation. I really appreciate it. And by the way, I think I will edit the recording of the lecture, and I will post it on Discord if I can, if there's enough. If it's small enough, but like most probably it will be on YouTube or
Right, yeah.
yeah. Thank you very much again. Bye.